So if you've ever been in a physics or a dynamics class, you might recognize these equations. What these equations describe is the position of a particle in terms of time, and it gives, the first one gives the x position of the particle and the second one gives the y position of the particle. You may have wondered where these come from, and it's really pretty easy to derive them, so I'm going to show you how to do it. So the first thing to do is to break up this velocity vector into its components. So right now we have v naught, and we're given some angle theta. So we know that we can break this up into vy and vx. Vx we know is going to be equal to v naught cosine theta, and vy is going to be equal to v naught sine theta, since it's in the y direction. So the next step is to start with the very basic of what we know. So the first thing we know is the acceleration in each direction that's acting on this particle. So the acceleration in the x direction is going to be equal to 0, and the acceleration in the y direction is always going to be equal to gravity, so negative g. So let's start over here with x. We'll do the x side first. So ax, acceleration we know can be defined as the change in velocity per rate of time. So dv of x of t, don't forget that it's a function of t, per time. So we know that this is equal to 0. So what we can do here is separate variables. So ax dt equals dv sub x of t, and we're going to integrate both sides. So we're going to integrate, we'll assume that we're starting at time equals 0, so we'll integrate from 0 to t on this side, and on this side we'll integrate from our initial velocity to the velocity at time t. So when we look at the left side, with the definite integral, we'll have a of x multiplied by t is going to be equal to v of t, v sub x of t, minus v naught sub x. So we know our acceleration in the x direction is equal to 0, so we can set this side equal to 0. And we're going to end up with v sub x of t is equal to v naught sub x. And up here, earlier we defined that v of x is equal to v naught cosine theta. So v naught cosine theta is equal to v of x of t. Now if we go over here to the left, to the right hand side, we can take the y, so we'll label this the y side, and we can do the same thing. We can know that ay is going to be equal to dv sub y over dt. We know that this is a function of time, so we can say dv sub y of t over dt is equal to negative g. Now if we separate variables, so dv sub y of t all over dt equals negative g, I'm going to separate variables. So this is actually going to go to the other side. We'll have negative g dt. We'll do the same thing. We'll integrate this side from v naught sub y to vy of t. And this side we'll integrate from 0 to t. So this side is going to be negative gt, and this side will be v sub y of t minus v naught y. So vy of t is going to be equal to negative g t plus v naught sub y. And earlier we defined that v naught sub y is equal to v naught sine theta. So we'll add v naught sine theta. So right now we have two equations for the velocity of x and y. Now we can integrate further and get the position functions that are here. So if we know that Vx of t is equal to dx of t all over dt, and we can set that equal to v naught cosine theta. When we do this, we can separate variables again, so dx of t equals v naught cosine theta dt, and we'll integrate again on both sides. We'll go from 0, assuming that we start at an initial position of 0, to x of t. So on the left-hand side, we get x of t equals, and on this side, we're going to go from time 0 to time t. So v naught cosine theta times t. And that right there will give us the equation that was up here. Now this initial x, we would have this initial x if we had integrated from x initial to x of t, but we integrated from 0 to x of t, so that eliminates the x initial from our equation. But, oops. Now we'll do the same thing on the other side. So if we set v sub y of t equal to dy of t dt equal to negative g t plus v naught sine of theta, we can separate variables and integrate again. So I'll start up here actually. So dy of t equals negative gt plus v naught sine theta dt. Put that in parentheses. And we're going to integrate this side from an initial position of 0, so same thing we did before, to y of t, and we'll integrate this one from, we'll integrate from 0 to t. So on the left hand side we get y of t equals negative gt squared all over 2 plus v naught sine theta multiplied by t. And that gives us the second equation, which is found here. Hope that makes it a little clearer. I suggest anytime you have any kind of particle motion problem like this, or projectile motion, you think about it this way rather than think about formulas. So if you have any questions, please let me know, and I appreciate your time.